Ever since I started this channel, one of the technologies that I've been using quite a lot is containers. And it occurred to me, I've never really explained how they work and why I find them so useful. So let's go and take a deep dive into the world of containers, right here on Jeff's Pie in the Sky. Hello once again, Pi geeks and techno nerds all around the world. My name's Jeff, and I'm an IT professional who's been in the industry for over 30 years. I've been using Raspberry Pi since they first came out, and I wanted to share with you some of the projects that I've done along the way. If you like what you see on this channel, please hit that thumbs up button, subscribe if you want to see more, and hit that notification bell so you can be told when I put a new video out. Let me know in the comments how you use Raspberry Pis, and if you've got any ideas for a project that you'd like to see me do in the future, put those in there as well. One of the big challenges in computing has always been deploying your software onto a production machine. Now, if you wind the clock back, it used to be very common that people would just install an operating system, install a whole load of application software, and hope that it all ran really well. If there ever came a point where they needed to upgrade a particular component or a particular piece of software, it could get really fiddly. Sometimes you had to unpick or change configuration or data files in order to get a new version working. Equally, if something catastrophic happened to the machine, you had to rebuild it again from scratch. You'd need to replace whatever hardware had failed, reinstall the operating system, reinstall all of your application software, and hope you didn't make any mistakes along the way. The other issue that always became quite difficult and quite expensive was horizontal scaling. Now, this is where you scale an application by adding more infrastructure. So as opposed to just adding extra memory or extra CPUs to your machine to make it run better, you actually add new machines to run your application, and then use maybe a device like a load balancer to spread all of the requests between them. Now, fortunately, in this day and age, most of these problems have been solved, or at least helped, by virtualization and the adoption of containers. So what's the difference between the two? Well, with a virtual machine, you've got an entire operating system that's running within a sandboxed environment. So specific CPU cores, memory, and storage are carved out to host that operating system, and it runs in its entirety within that environment. Containers are conceptually quite similar. You still end up with a sandboxed environment. However, they only run the processes that you actually need in order to run your application. So you don't have the entire operating system running within a container. You just have your applications running. So they're far more lightweight in terms of runtime. And so containers are basically designed to be reusable components that you can stitch together in order to build a fully functional application. Now, that's not the only use case for containers. There are several others. I'll cover some more later, but I hope you understand the basic principles. Now, through this video, I'm just going to show you some examples of how I run containers and some of the tricks that I can use with them in order to build final solutions that really are very effective. So let's get going. Now, before you can start playing with containers, you need to install some software that lets you play with them. Now, there are many different tools that you can get to do this. For example, Podman, Builder, Rancher, Vagrant, Kubernetes. But probably the most famous software is Docker, and it's certainly what I've been using longer than anything else. So I'm going to install Docker on my Raspberry Pi here so that I can show you how it all works. Now, in terms of hardware here, it's just a Raspberry Pi 4, and for its operating system, I'm running Raspberry Pi OS 64-bit Lite. To install Docker, I'm just going to run this command here, curl -lowercase s, uppercase S L, space https://get.docker.com. I'm then going to pipe the output of that into sh. Now that Docker's installed, I have to make one slight change before I can make use of it. I have to add my current user, which is Pi, to the Docker user group. I can do that with this command here, sudo usermod -a G Docker Pi. Now that's done, I just have to log out and log back in again. Now that's done and I'm logged in again, I can prove that Docker is running okay by running this command here, docker run hello-world. This goes ahead and downloads a Docker container that just contains the message that you can see has been displayed there. So this proves that our Docker system is working just fine. So now we've got Docker up and running, let's build our first container. Now I'm not sure if any of you have ever installed Apache's web server before, but it can be a little bit fiddly to configure. You've got to define what site you want to be enabled, and then you've got to configure the location of where your data is. And it's basically a complete faff just to get a simple web page to show up. So let me show you how Docker can really simplify this process. I've created this super simple HTML page here. It does nothing more than display the text Jeff's pie in the sky. And I'm going to host this on an Apache web server running in Docker. To achieve this, I've had to create this thing called a Docker file. And a Docker file is basically just a build instruction to Docker to build a container. This first line here defines what's called the base image. Now there are a ridiculous amount of different container images out there that you could use as your base image. A good place to go to find Docker images is hub.docker.com. It's got a whole repository full of different images that you can use either for your own application or to build upon. And this includes everything from basic operating system bases, such as Alpine Linux or Ubuntu Linux, of various versions, all the way up to fully fledged applications. For example, you could get a Postgres database Docker image. This is the page for the HTTPD image that I want to use. And specifically, I'm using this version here, the 2.4-bookworm. So the operating system matches what I'm running on my Raspberry Pi, although that's not critical. You don't have to do that. I could pick one of these Alpine Linux versions. What's really great about Docker Hub is that most of the containers listed on it give you really good instructions on how to use it. And this example here is really what we're following. It just says, take your HTML files and load them under the user local apache2/htdocs directory within the container, and then you should be able to serve them out. And that's exactly what I'm doing here. I'm just adding my index.html file under the htdocs directory, and then when we run up the container, we should find that that's served up with no problem. So how do I build my container? Docker build forms the basis of the command that we need to run here. The --rm parameter basically says that I'm going to remove what are called intermediate layers. Now, I won't get too bogged down with that right now. Just suffice to say, it's normally a good idea to specify that, as it will save a load of disk space, especially if you build particularly complex containers. The next thing I want to do is give my container a tag or a label, and that's what this -t option does. The PITS part, or pie in the sky, is just identifying that this is a container that I'm building. All of this is just entirely free text, so you can format these tags however you like, but just bear in mind there are some caveats. You can't use spaces, and the use of things like forward slashes and colons and dots here can have some special meaning depending on where you put them. So effectively, all I'm saying here is that I'm creating a container that's part of my stuff, hence I've put the PITS/. I'm calling this test, and I've given it a version number that is separated from the name via the colon of 0.0.1. The -f Docker file specifies where my build instructions are. And the final dot here just means that all of the resources that it will need to build the container are here in the current directory. And that has all completed successfully. Now I just need to run my container. And I can do that with this command here, docker run -p 80:80 pits/test:0.0.1. Since this is running a web server, I have to tell the container which ports I need to be able to see. Since it runs kind of like a virtual machine, left to its own devices, it'll run within its own little sandbox. And so I wouldn't actually be able to see the web server. This option here effectively lets me map that port through to the host. So I'll be able to connect to that port 80 directly. So here, I've run up our web server and everything's running just fine. If I now just enter the name of my Raspberry Pi into my browser, you can see that it's just showing me the rendered web page. And switching back to the terminal, you can see the request that hit the Raspberry Pi. If I hit Ctrl C, it will shut the container down. And it's exited out. Now there you could see that my web server was running in the foreground, and it was always showing me the log messages that were coming out of the web server. If I wanted to run my web server entirely in the background, I can just add this -D option to the Docker run command line, and this then just runs the container in the background. But how do I know if it's running? Well, you can always make Docker tell you what's running with the Docker ps-a command. And here you can see it's telling us that there's one instance of our container that is up and running, and there's one instance of our container that exited about a minute ago. Since our container is running, I can still go back to my browser, refresh the page, and I can still see it rendering my web page. Now, what's really remarkable about this is that because the whole runtime environment is built into the Docker container, no matter what happens with my host operating system, no matter what I install, so long as it's capable of running Docker containers, my container is guaranteed to be able to run successfully because it doesn't really need anything on the host layer. Everything it needs to be able to run is built into the container, so it's incredibly powerful. But given it's running in the background now, how do I stop it? In order to do that, you need to be able to identify the running container. And there's a choice here between two fields you can use for that. You can either identify a container by its ID or by a logical name. If you don't specify a name to use for your container when you run it up, it will just create one like what it's done here. And that's guaranteed to be unique. But then I can stop the container with docker stop, and I could either put in the name as you can see here, or I could put in the ID as you can see here. Either will work. If I now run docker ps-a again, now both containers are in an exited state. Now you can probably imagine that over time, if you're always starting and stopping containers, this list of exited containers could get quite big. And you can clean all of that up with this command here, docker container prune. You just have to confirm that that is what you want. And now if I run docker ps-a, I get absolutely nothing returned. If you want to provide a name for your running container, you just have to specify this --" name parameter when you run it. And here you can see that now the name is listed as test. And I can use that name if I want to stop the container. The other way that you can clean up exited containers, if you want to do it one by one, is by using the docker rm command. Now, just like with docker stop, you can either use the name of your container or the ID. And you can see that that's cleaned it up again with absolutely no problem. Now, the other great thing about containers is that you can run the same container multiple times, and you don't have to do this on separate hardware. So if you want to have multiple instances of your web server running, it's really easy to do it. So here I can run up an instance of my web server. And then if I want to run up a second instance, there's a couple of things I've got to change. I've got to provide a different name for my container because you can't have two running containers with the same name. I've also had to change the port that the second container is listening on the host system. This is because you can only have one process listening on a given TCP port. So because I'm going to be running two web servers here, one of them has to be running on a different port. However, you can now see that I'm running two instances of my web server, one that listens on port 80, the other one that listens on port 81. Back here in my browser, if I just navigate to the host name of my Raspberry Pi, it will by default be connecting to port 80. However, if I update this to specifically go to port 81 on that same machine, there you can end up, it serves up the same web page. So what you can see from this is that if you wanted to have multiple containers serving up all different types of content, you can do it. And using Docker containers like this, it's far easier to do it than if you had to go through configuring Apache's web server yourself directly. Now, all of this process of building your own Docker container, where you add files into it and then run up applications that make use of those files, is all well and good, but it is a bit limiting. What I've got here is an updated HTML page, and you can see it just shows a slightly different message. Now, if I wanted to have one container that shows the original index.html page, and then I want a second container that shows this updated message, I could go through creating two different Docker files, so I'd have two independent containers that are very specific. Now, most of the time, but certainly not always, a Docker container is designed to be a generic reusable component where the container is built with a generic engine, and then you provide the data that it has to process. Now, that's not to say that you can't have very specific use containers that do a particular job with particular built-in data. That is fine, but more often you'll find containers being built in a very generic way, with the idea being that you pass data into them. Now here I've got a new Docker run command. Rather than running the container that I built earlier, I'm going to instead run the container that I originally used as a base image within my Docker file. So this is basically just the Apache HTTPD web server. I've also added this --rm parameter, and what this means is that when the container stops, it will automatically delete itself from the process list. So I wouldn't need to do a docker rm command again to delete it from there and clean up. And I'm going to make this listen on port 80 on the host. So now that's running. And if I go to my browser, I can see that is being served up no problem. Now this time I'm going to run up a second instance, and it's running that exact same Apache container. But this time I'm volume mounting the index.html.2 file as /user/local/apache2/htdoc/index.html within the container. And just like before, I've had to change the port that this is listening on just to make it unique. So now that's running okay. And within my browser, if I now navigate to http:// the name of my Pi :81, you can see it displays the other message. And this is despite the fact that I'm running the exact same container in both cases. I've just changed the data that is mapped into the container, but I've done that at runtime, just by using this volume mounting technique. And as well as being able to use this to add files into your container at runtime, you could also use this to override files within your container to change its behavior. It's really very powerful. And just to show that --rm functionality, in my docker ps-a command, I already had those other containers I was running before in an exited state, and there were my two new containers in an up state. Now I've stopped both of those containers, and because in each case I specified the --rm option when I ran it, now if I run docker ps-a, you can see I still see the older exited containers, but I don't see the newer ones, because they cleaned up after themselves as soon as they exited. But now I'm going to clean up the other ones by once again running docker container prune. And now everything's all nicely tidied up. Now let's start doing something that's a bit more complicated. Let's start linking containers together. Now what I've done here is I've pulled out of GitHub my Slideshow project. This was from a video that I did in December 2023. This brings several containers together to provide a web application that you can use for showing a slideshow of images on a small display connected to your Raspberry Pi. The idea at the time being that you could hang that on your Christmas tree. Now, one aspect of this is that as well as the web application that I'm running, which is implemented as a Python Flask application, there's also a database which is hosted with MySQL. So I need to get all of these different containers running together. Now I could run up each container individually using a docker run command, but already, as you saw in the previous commands, they get pretty unwieldy pretty quickly. And especially if you're mounting an awful lot of volumes, you could end up with a very complicated multi-line Docker run command. This is where orchestration engines come into play. Now, the one that I like to use is Docker Compse, but there are many available. But let's take a look at how much simpler this makes the configuration of all of these different containers. Docker Compse works from config files written in the YAML format. So what I have here is a whole bunch of different containers that are configured to work together. Looking initially at this one, this is our database container. Up here against image, you identify the name and the version of the container that you want to run. In this case, I want to run the latest version of MySQL. Now, Docker Compse and other orchestration engines also allow you to say what's going to happen if your container exits, especially if it exits unexpectedly. So if my database did crash, this restart always directive will make Docker Compse automatically start it up again. The container name directive in Docker Compse is effectively the same as the -name parameter that I was providing in the Docker run command line earlier. It just lets you give your container a friendly name. The user defines what user the application runs as within my container. In this case, it's just using whatever is at user ID 1000. Like on my host system, that would be the user pi. Here I specify the volume mounts that I want to use for this. And I do actually need to make a slight edit to this because the directory that I have this checked out to is called Slideshow, not Slideshow main. So I'll edit this just prior to me running it. Now, the MySQL container is really nice because it lets you define environment variables that can be used within the container to perform some initial configuration. One of these is for setting the root password within MySQL, so you don't have to have anything baked into the container itself. The other thing that Docker Compse lets you do is write these health check scripts. And this basically says, if anything's depending on this container, don't allow that to start up until you've proved that the database is up okay. Up at the top, I then have another container that's running software called Adminer. And if you've never heard of it, it's basically just a web interface into various database engines. You can see here, I make that listen on port 8082. And I also specify this depends on option, where I then point that at the database container. So this adminer container won't start until the database is up and running. Down here in Slideshow, this is my main application container, where here again I have the image name identifying the name of the container. And again, I'm going to need to make a slight edit to this before I run it because I've named the container actually something as slightly different on my Pi here. Again, it depends on the database container, and here I use that volume mounting technique, and this basically allows me to persist any images that I upload into the application. So if I stop the container and then start it again, I won't lose any data. One of the beautiful things about containers is that they are immutable. While they're running, you could theoretically log into them, make all kinds of changes, upload data into them, download data from them, whatever you like. But if you stop the container and you restart it, it would go back to its original state again. So if you do need to persist data, then you need to use volume mounting to do it. So basically, any data that gets written into the /flask/static/images directory within the container, I would be able to see on my host system, on my Raspberry Pi, in /home/pi/slideshow/uploads. I'm going to get rid of that /main bit in a second. And then I expose this on port 80 on the host system, and that gets mapped through to the Flask port, which is port 5000 within the container. I then have this Slideshow client container, and this is the thing that basically shows the current image as a full screen display from the Pi. So I've changed the name of the directory here that I use for volume mounts. I've corrected the name of the containers that I built for this particular case. I didn't realize that I'd actually named them differently from before when I first downloaded them. And everything should be ready to go. Just before I do start this up, I do want to point out something that's really quite clever. If we look at the test that's being run on the Slideshow container here, you can see that the host name it's using is Slideshow. And this just matches the container name that is defined here. And indeed, if I wanted to access resources on other containers, I can just access them via their container name. Just as an example, the Slideshow container has got a depends on clause on Slideshow database, so it can access the database. However, internally in the configuration file, where it has to specify the host name of the database, it can just access it as Slideshow DB, since that's the name of the container. So this makes linking all of the containers really, really simple. So I can run this with the command Docker Compse -f, the name of the YAML file, up, and then I specify -d so that everything runs in the background. And now everything's running. If I go over to my browser, I can now navigate to the application, and if I click the link to upload an image, I can then upload an image into the website. And if I switch to the output of my Raspberry Pi here, you can see that it is now showing that image full screen. And I can stop the whole application just by using the command Docker Compse -f, the name of my YAML file, down. And that shuts everything down. And if I run docker ps-a, you can see that everything's cleaned up after itself. Just to illustrate what I was talking about earlier about data persistence, here if I go to the uploads directory, which is the directory that I volume mounted into the container that I was uploading images into, you can see the file is now left there, even though all of the containers have been shut down. And it's exactly the same with my database data directories. All of the tables and all of the data that was in them was volume mounted in from the host. And therefore, even though everything's shut down, all of that data still exists. So next time I start up the MySQL container, it won't need to reinitialize the database again, and all of my pre-existing data will still be there. Now, one thing I mentioned earlier was the concept of layers within a Docker container. Every time you run a command within a Docker file, it will create a new layer to run that command in. Now that conceptually may not make a lot of sense right now, so let me show you what I mean. In this Docker file, I'm using a basic Ubuntu container as a base. I'm updating it, I'm then installing Python 3, and then I'm installing Apache 2. Now what I'm going to do is I'm going to turn off what's called the Docker build kit, and this allows us to see what's going on under the hood a little bit more clearly. So just by running this command export docker build kit equals 0, I can turn off that Docker build kit. Now, if I run my Docker build command to build that Docker file, let's see what happens. Okay, so now my container is built, and I'm going to run it with this slightly modified Docker run command. The -it option here says that I want it to be an interactive session, and the -entry point option allows me to override what runs within the container at first. In this case, I just want it to run the bash shell, but then I can just provide my Docker container name as normal. So if I run this command here to see if I've got Python 3 installed, you can see that that is showing that it is installed. Equally, if I look for the Apache 2 package, I can see that that is installed as well. So the final version of my container is exactly what I'd expect. However, if I scroll back up again through the build process of the container, what I can see here is the point at which I installed Apache 2. And just before then, I have this line here where it's giving a weird looking ID. If I grab a copy of that and I use that ID rather than my final container name, I still end up inside an Ubuntu container. I still have Python 3 installed, but now because this container ID is referencing the point in time before Apache 2 was installed, I can no longer see it. And this is what's called layers within a Docker container. Every time you run a command, a new layer is created, and every layer gets its own ID. Now this is quite a funky concept, but it can lead to a real big problem. To illustrate this concept of layers, I'm going to build this Docker file here. It uses Ubuntu 24.04 as a base, and I then use the dd command to create a really big file, in this case about 50 megabytes of data on the file system. So if I build my Docker image, and I then look at the images that I've got on the system, you can see that my Docker container is about 50 megabytes bigger than the original Ubuntu 24 image. And that's exactly what we'd expect. I've now got this second Docker file, and here I actually remove that big file. So let's build this and see what happens. What's really weird here is that we did actually remove that big file, but if we look at the size of our container, it's just as big. It's still 152 megabytes. So why is this? Well, it's because the layer where the file was created, up here in step 2, still contains all of that data. And so irrespective of if we subsequently delete it, it won't affect the size of the eventual image. But there is a way that we can work around this. So here I've got a last Docker file. Initially it looks exactly the same, but I've just given my initial setup an alias of builder. I then say from scratch, i.e. from a completely empty container, I want to copy everything over from builder into this container. And what I'll end up with is a container that's only got a single layer in it. And it will be the final state of the files from the original builder. So it won't have that big file anymore. Let's build that and I'll show you what I mean. Now if I look at our Docker images, my version 0.0.3 is now back down at 101 megabytes again. Effectively the equivalent of just the Ubuntu 24.04 Docker image. It's no longer got that 50 megabyte file lying around. So if you're ever in a situation where you're building a Docker file, it constructs tons and tons and tons of layers, and you end up with a Docker image that's absolutely huge. You can use this multi-stage build technique to end up with only the final outcome, and you can lose all of that bloat. And so there you go, a quick whiz around the world of Docker and containers. Now in a future video, I'm going to be building a cluster, and I'm going to be using software called Kubernetes to orchestrate containers running across that cluster of different Raspberry Pis. So if you're interested in seeing that, do make sure you subscribe. But that's it for this video. Once again, if you like what you see here, please hit that thumbs up button. Subscribe if you do want to see more, and hit that notification bell so you can be told when I put a new video out, including that one about Kubernetes and clustering. Let me know in the comments how you get on with Docker, or indeed any other software that you use to run containers. And if you've got any ideas for projects that you'd like to see me do in the future, put those in the comments as well. Thanks so much for watching till the end, and until next time, bye for now.